J. Robert Oppenheimer, Namur, April 22, 1904 to February 18, 1967, was an American theoretical physicist who was professor of physics at the University of California, Berkeley. Oppenheimer was the wartime head of the Los Alamos Laboratory and is among those who are credited with being the father of the atomic bomb for their role in the Manhattan Project, the World War II undertaking that developed the first nuclear weapons. Oppenheimer was among those who observed the Trinity test in New Mexico, where the first atomic bomb was successfully detonated on July 16, 1945. He later remarked that the explosion brought to mind words from the Bhagavad Gita. Now I am become death, the destroyer of worlds. In August 1945, the weapons were used in the atomic bombings of Hiroshima and Nagasaki. After the war ended, Oppenheimer became chairman of the influential General Advisory Committee of the newly created United States Atomic Energy Commission. He used that position to lobby for international control of nuclear power to avert nuclear proliferation and a nuclear arms race with the Soviet Union. He opposed the development of the hydrogen bomb during the 1949-1950 governmental debate on the question and subsequently took stances on defense-related issues that provoked the ire of some factions in the U.S. government and military. During the Second Red Scare, those stances, together with past associations Oppenheimer had with people and organizations affiliated with the Communist Party, led to him suffering the revocation of his security clearance in a much-written-about hearing in 1954. Effectively stripped of his direct political influence, he continued to lecture, write and work in physics. 9 years later, President John F. Kennedy awarded, and Lyndon B. Johnson presented him with the Enrico Fermi Award as a gesture of political rehabilitation. Oppenheimer's achievements in physics included the Born-Oppenheimer approximation for molecular wave functions, work on the theory of electrons and positrons, the Oppenheimer-Phillips process in nuclear fusion, and the first prediction of quantum tunneling. With his students he also made important contributions to the modern theory of neutron stars and black holes, as well as to quantum mechanics, quantum field theory, and the interactions of cosmic rays. As a teacher and promoter of science, he is remembered as a founding father of the American School of Theoretical Physics that gained world prominence in the 1930s. After World War II, he became director of the Institute for Advanced Study in Princeton, New Jersey. Oppenheimer did important research in theoretical astronomy, especially as related to general relativity and nuclear theory, nuclear physics, spectroscopy, and quantum field theory, including its extension into quantum electrodynamics. The formal mathematics of relativistic quantum mechanics also attracted his attention, although he doubted its validity. His work predicted many later finds, which include the neutron, meson and neutron star. Initially, his major interest was the theory of the continuous spectrum, and his first published paper, in 1926, concerned the quantum theory of molecular band spectra. He developed a method to carry out calculations of its transition probabilities. He calculated the photoelectric effect for hydrogen and X-rays, obtaining the absorption coefficient at the K-edge. His calculations accorded with observations of the X-ray absorption of the Sun, but not helium. Years later it was realized that the Sun was largely composed of hydrogen and that his calculations were indeed correct. Oppenheimer also made important contributions to the theory of cosmic ray showers and started work that eventually led to descriptions of quantum tunneling. In 1931, he co-wrote a paper on the relativistic theory of the photoelectric effect with his student Harvey Hall, in which, based on empirical evidence, he correctly disputed Dirac's assertion that two of the energy levels of the hydrogen atom have the same energy. Subsequently, one of his doctoral students, Willis Lamb, determined that this was a consequence of what became known as the Lamb shift, for which Lamb was awarded the Nobel Prize in Physics in 1955. With his first doctoral student, Melba Phillips, Oppenheimer worked on calculations of artificial radioactivity under bombardment by deuterons. When Ernest Lawrence and Edwin Macmillan bombarded nuclei with deuterons, they found the results agreed closely with the predictions of George Gamow, but when higher energies and heavier nuclei were involved, the results did not conform to the theory. In 1935, Oppenheimer and Phillips worked out a theory, now known as the Oppenheimer-Phillips process, to explain the results. This theory is still in use today. As early as 1930, Oppenheimer wrote a paper that essentially predicted the existence of the positron. This was after a paper by Paul Dirac proposed that electrons could have both a positive charge and negative energy. Dirac's paper introduced an equation, known as the Dirac equation, which unified quantum mechanics, special relativity and the then new concept of electron spin, to explain the Zeeman effect. Oppenheimer, drawing on the body of experimental evidence, rejected the idea that the predicted positively charged electrons were protons. He argued that they would have to have the same mass as an electron, whereas experiments showed that protons were much heavier than electrons. 2 years later, Carl David Anderson discovered the positron, for which he received the 1936 Nobel Prize in Physics. In the late 1930s, Oppenheimer became interested in astrophysics, most likely through his friendship with Richard Tolman, resulting in a series of papers. In the first of these, a 1938 paper co-written with Robert Serber entitled On the Stability of Stellar Neutron Cores, Oppenheimer explored the properties of white dwarfs. This was followed by a paper co-written with one of his students, George Volkoff, on massive neutron cores, in which they demonstrated that there was a limit, the so-called Tolman-Oppenheimer-Volkoff limit, to the mass of stars beyond which they would not remain stable as neutron stars and would undergo gravitational collapse. Finally, in 1939, Oppenheimer and another of his students, Hartland Snyder, produced a paper on continued gravitational contraction, which predicted the existence of what are today known as black holes. After the Born-Oppenheimer approximation paper, these papers remain his most cited, and were key factors in the rejuvenation of astrophysical research in the United States in the 1950s, mainly by John A. Wheeler. Oppenheimer's papers were considered difficult to understand even by the standards of the abstract topics he was expert in. He was fond of using elegant, if extremely complex, mathematical techniques to demonstrate physical principles, though he was sometimes criticized for making mathematical mistakes, presumably out of haste. His physics was good, said his student Snyder, but his arithmetic awful. After World War II, Oppenheimer published only 5 scientific papers, one of which was in biophysics, and none after 1950. Murray Gell-Mann, a later Nobelist who, as a visiting scientist, worked with him at the Institute for Advanced Study in 1951, offered this opinion: he didn't have Sitzfleisch, sitting flesh, when you sit on a chair. As far as I know, he never wrote a long paper or did a long calculation, anything of that kind. He didn't have patience for that. His own work consisted of little aperçus, but quite brilliant ones. But he inspired other people to do things, and his influence was fantastic. Oppenheimer's diverse interests sometimes interrupted his focus on science. In 1933, he learned Sanskrit and met the Indologist Arthur W. Ryder at Berkeley. He read the Bhagavad Gita in the original Sanskrit, and later he cited it as one of the books that most shaped his philosophy of life. His close confidant and colleague, Nobel Prize winner Isidore Rabi, later gave his own interpretation. Oppenheimer was overeducated in those fields, which lie outside the scientific tradition, such as his interest in religion, in the Hindu religion in particular, which resulted in a feeling of mystery of the universe that surrounded him like a fog. He saw physics clearly, looking toward what had already been done, but at the border he tended to feel there was much more of the mysterious and novel than there actually was. Away from the hard, crude methods of theoretical physics into a mystical realm of broad intuition. In spite of this, observers such as Nobel Prize-winning physicist Luis Alvarez have suggested that if he had lived long enough to see his predictions substantiated by experiment, Oppenheimer might have won a Nobel Prize for his work on gravitational collapse, concerning neutron stars and black holes. In retrospect, some physicists and historians consider this to be his most important contribution, though it was not taken up by other scientists in his own lifetime. The physicist and historian Abraham Pais once asked Oppenheimer what he considered to be his most important scientific contributions. Oppenheimer cited his work on electrons and positrons, not his work on gravitational contraction. Oppenheimer was nominated for the Nobel Prize for Physics 3 times, in 1946, 1951 and 1967, but never won.